Dimitri. Right. When submitting the talk, I wasn't sure about what neutron star transient I'll be talking about, so I kept it vague. So diving right in, I'll be talking to you about some of my simulation work regarding one type of neutron star transient, namely magnetized giant flares. So just to give you some overview of what the problem is, magnetars are young neutron stars. They are very slow spinning, periods of a few seconds or so. And the unique trait is that their magnetic fields are exceedingly high, 10 to the power 13 and above. Now, giant flares, these are extremely short, bright X-ray flares going up to around 10 to the power 46 ergs in a very short span of time, and then slowly decaying over seconds to minutes to probably hours time scales. Now, a lot of this work was done originally in the early 90s by the esteemed gentleman in the front here. Now, excitingly, because these events are responsible for some of the more brighter, let's say explosive events related to neutron stars, they can also be possible progenitors of fast radio bursts coming from the cosmic distances. Now, the idea is to see like what type of mechanisms can actually form these type of flares, starting from, let's say, just a non-rotating neutron star. Right. Okay, so we usually the phenomena that's linked to such events are known as crustal twists, where mostly the idea is that you start off with some event on the magnetar, inside the magnetar, which gives rise to some sort of twist on the surface. So, for example, one can draw up a cartoon picture like this, where that's the neutron star itself on the magnetar, and then you just have to twist up or shear up the surface in a certain way. Now, when you start twisting up the surface, you immediately send waves along the dipolar field that's surrounding the neutron star, and these begin to twist up the dipolar field, generating azimuthal fields. Now, this is just an example of what happens. So these are B at the azimuthal field contours. So the twist over there, starting from one side, slowly travels on the other side and starts bouncing back and gradually builds up over time. Now, what happens is, because as we keep twisting, we are injecting energy into the magnetosphere of this neutron star. So eventually, at some point, the magnetosphere gives way and the dipolar field starts expanding. At some point, these inflating flux tubes become unstable, generating this sort of very large-scale explosive events, previously done by ERG and Jensen's papers. So that's the neutron star, for example, over there. These are the twisted field lines. And then you see one big inflated field line over here, which generates a lot of Poynting flux upon, let's say, the release upon, let's say, reconnection maybe. Now, in each of these cases, the ejected electromagnetic pulse that was released was of the order of 10 to the 48 ergs per second of that luminosity. Assuming that you have we start with a 10 to the 15 Gauss magnetic field, which is enough to actually explain the energetics of the particular system that we are talking about. However, these simulations miss out on a crucial element. These are all force-free models, which means that they were neglecting the effect of the plasma, which means that what these models successfully account for are the electromagnetic energies that are released from the system, but not what happens to the reconnection heated gas, especially the gas that's either going out or coming back in. So that's what I'll be dealing with using magnetic hydrodynamics instead of force-free modeling. Now, this is just an overview of my code. So this is a ideal collisional fluid code, well, MHD. It's GRMHD, but in this particular problem, I neglect the GR, just have special relativistic MHD. And of course, like because it's MHD, I cannot capture any kinetic effects. And some of the perks of this particular code is that it is GPU accelerated, so you can really push up your grid resolution and also go to pretty long time scales. It also gives you the ability to hone in on specific regions in the mesh using adaptive mesh refinement. And for example, like all of these perks allowed us to go perform a 2000 cube simulation. This is one of the largest GRMHD simulations ever performed on 6000 V100 GPUs on the Summit cluster. And yes, Bart published this paper on 22. I think we already may have seen images from this paper during this conference sometime, but I forget when. Yes, so because this is a MHD, but I'm tackling a neutron star problem, the large magnetic fields that I need won't be able to cannot be tackled by this code. So for that, I had to mock up a force-free hydrodynamics part as well, where which would be able to tackle the large magnetic fields that I need, or rather the large magnetizations that I need, or low plasma betas. So this is basically I'm still using MHD, but then I can mock up force-free electrodynamics by constraining what my thermodynamics, fluid thermodynamics is. This is a method taken from Parfait and Tchaikovsky 2017, but then pushed to very, very large grid resolutions. So for example, I was successful in doing a pulsar simulation, a 3D pulsar simulation on 3000 GPUs, where I was able to resolve the current sheet well enough to actually see instabilities, like tearing instabilities forming on the pulsar current sheet. But yeah, so taking this code, this is the initial setup that I have. On the left over there, that's the azimuthal field over the polaroidal magnetic field, starting from B is equal to 0. That's the star over there, and those are the lines indicate the dipolar field lines. This is the middle panel is just a zoomed in version of that. So we'll be focusing on the what's going on in the inner magnetosphere as the simulation evolves, and then also we will be looking at the thermal energy of the fluid in the magnetospheric region again. While this part we will be zooming out to what's going on larger and larger scales. We restricted ourselves to performing 2D simulations because we wanted to know exactly what's going on instead of driving head-on into 3D, especially because we were tackling MHD for such a high magnetization. So for example, our cold magnetization was around 500, and our background plasma beta was around lower than 10 to the minus 8. We had to really make sure that nothing blew up in the simulation as such. Right, so we begin twisting up the fields, and you see that the azimuthal field becomes unstable and balloons up. And at some point, there's reconnection going on in the midplane, and you see hot gas coming back to the inner magnetosphere, while on the larger scales, there's, you can look at this again. On the larger scales, there's a huge bubble that's released, or ejector that's released, filled with this azimuthally dominated field. At the end of the simulation, we still had some amount of azimuth twisted field lengths left in the inner magnetosphere, which I'll talk a bit about as well. Right. So that's the ejected electromagnetic pulse that we saw before from Marman et al. As well as from Wan et al. This also carries energies of around 10 to the 46 ergs also. This is the remnant field that stays in the inner magnetosphere after the giant flare has erupted out and the magnetosphere starts closing back in. The remnant field may power matter persistent emission, but I'm not an expert in that. It does have a lot of energy stored up in there as such. So there may be persistent emission happening over long time scales. Now the more interesting part is this trapped fireball, which is the first time that we were able to see using MHD. This is really heated up gas. I think of order, the temperatures of order 1 in relativistic units. On the larger scales, the ejector that is flying out relativistically. So that's the ejector going out. It's filled with azimuthally dominated gas, but it's also cold. So the middle panel again is showing the fluid thermal energy. You can see like that's the ejector over there. And you're able to see the field lines, but so that's the ejector head over there, and the colored region over here. That's the ejector tail, which is being filled with the reconnected gas. So in addition to having a cold ejector head, you also have a hot ejector tail. Now, the third panel shows the Lorentz factor of the entire system. So the ejector tail has hot relativistically moving gas. The ejector head is also moving relativistically, more or less. And then we see a spherical shell moving out together with the ejector head. Yeah, so that's the ejector head, hot ejector tail, in a manner as a compressed front. So this region, in fact, is quite interesting because it doesn't have any guide field, so to say. So it can be, there can be efficient particle acceleration going on over there once it shocks, which it will probably eventually do once at very, very large distances. In the simulation itself, we reached Lorentz factors of around 10 to 15 in this region. But of course, there's now this region is still continuing to accelerate because we haven't reached square root of sigma yet, which is around, well, sigma is 500, so square root of sigma is around 20-ish. Right. So in terms of energetics, the x-axis over here shows the time. The y-axis over here shows the fractional energy in terms of the initial dipolar energy. So the orange line is the is the electromagnetic energy. So initially it rises up because we're injecting energy via the twist, and then at some point reconnection happens, and we stop twisting at that point. So we stop injecting energy, and there's an exponential decay of the magnetic field, which decays to some small value, which I'll talk about in a bit. But the interesting part is that this is the energy contained within 30 stellar radii. So all of the ejected energy that's calculated from the ejected flux inside of 30 stellar radii, right? So this first part, that's the ejected electromagnetic energy. That's around 10 to the 46 hours, which is the same thing that we saw in the force field simulations. This can potentially power FRBs. At least it contains the energy to do so, either via shocks or by interactions with the magnetic wind or current shield much further away. The ejected thermal energy, that's the ejector tail. That forms the giant flare, which forms which gives us the X-rays and the gamma rays, which is also of the same order as the electromagnetic energy. Next, the remnant electromagnetic energy is around 1 order smaller, and the fireball, which is the hot region in the inner magnetosphere, that's again of the same order as the remnant EM energy. Now, how do we explain this giant flare observation using the simulation? Well, first we have the initial peak over there, that's 10 to the 46 hours, which is what we wanted. And it's coming from the hot tail over here. And then the trapped fireball will extend, or should extend, hopefully diffuse, give off emission slowly over a few minutes or so, as per this. It certainly has the energy to do so because it has 10 to the 45 joules, and what we need is around 10 to the 44 joules or so. The pulsations over here, those indicate that those are around 8-second pulsations over here, and that indicates the period of the magnetar, which also says that what we need actually is a non-axis symmetric fireball instead of what we have over here. So that will also bring down the total energy of the system. In terms of this particular project of giant flares, what we succeeded in doing is explaining the energetics of one particular system to some satisfactory amount. But we need to do 3D simulations because, well, 3D is obviously much cooler. Thank you. And you additionally get 3D instabilities such as kink instabilities going on. So this is just a representation of one such simulation that we are trying out now. Another thing to try out would be other quick geometries, possibly twist field lines closer to the polar region so that we get longer timescale flares, and also bring in radiative physics. Because of the magnetic fields involved, the opacities that will be created on reconnection would basically produce optically sick gas coming back to the inner magnetosphere and going out as well. So you need optically sick, optically sick treatments over there. I just wanted to flash this. This is not a new talk. Because of the system we cooked up, we could also treat actual gas accreting onto a neutron star, which can be used to treat X-ray pulsars as well. This is also an interesting topic of mine because I come from a black hole background as well, so there's some familiarity there. And that's something that one can see. Like, so over here, we have similar tori that we saw in the black hole simulations before, but then replace the black hole with a neutron star. So it has its own dipolar field, and there's accretion via these columns over here, in this case. Now, sometimes we see there are strong magnetospheric disk interactions similar to what we see in black hole simulations, these magnetically acid disks. So on the left over here, that's the equatorial plane of a neutron star simulation, where this inner part is the inner magnetosphere, and the outer part is one of these magnetospheric arms going out. And over here is a black hole simulation, where this is one of these large-scale current sheet flares that we see in magnetically acid disks. I just wanted to show this one cool movie I had, where I have an oblique pulsar going around, moving, and then there's this accretion disk trying to accrete onto it, but it's not letting it. And if you carefully see over here, there's the current sheet, the pulsar current sheet that's sort of whipping the disk about. So potentially this system can create both strike winds, which is important for polarization, but also because the current sheet whips about the disk in this particular system and strips off gas, so there might be also QPO effects coming off in the wind region. That's something interesting that I wanted to show. And I'll end with the conclusion slide over here. Thank you.
Thank the speaker.
Thank you for the talk. I have two questions. Could you back up one or two? Yeah, this one. Next slide, sorry. Yeah, could you explain what is the geometry? What are we looking at? Where is the axis of rotation? I'm confused.
Sorry, I went a bit quick over here. So this is a vertical XZ slice. The axis of rotation is the Z-axis over here, and the magnetic axis, the dipolar axis is something like 30 degrees offset to that. And
that disk is inclined at some random.
Yeah, this disk is also inclined at some random radius.
But
sorry, at some random angle.
What is that angle? Why is there an angle?
Well, this is just one thing that I was trying out in the sense that oblique pulsars are interesting when you have accretion force coming onto it because it can potentially open up more field lines. And depending on the geometry of the disk, you can potentially open up more field lines. So that was the idea over here.
Okay. Second question, if I may. When you dissipate magnetic energy in a high sigma situation, when we do it in particle in cell, I usually expect about half of the energy to go into plasma. So we end up with sigma water 1. Is that still the case in MHD? Like when I look at your fireball, how much thermal energy is there? And is there a hard
of
rule
order
on
B square.
What?
Of order B square.
So sigma water 1 in the closed zone.
Roughly speaking, yes. There's also the azimuthal field in there, so it's not exactly 1. The azimuthal field is also pretty strong.
Is this expected? Is this amazing, or is this an artifact of something?
The azimuthal field?
Well, like, I mean, you dissipate it somewhere else, right? And then you ended up with a closed field lines full of thermal plasma. Why do they have to be of the same order of magnitude?
Well, it gains their order of magnitude where they dissipated, right? So at the reconnection spot, which is further along at some large distance, the gas gains a certain internal energy, and then brings it back, and which then and the gas then closes up inside of the closed zone. Maybe yes. So the gas over here. So let's say it reconnects over here, it comes back in, hits the closed zone, and goes up and sort of circulates about energy. But there is, there is a remnant of that energy that's coming back here, so, right?
All right, thanks.
You have a question from Chris? Yeah. Just first a quick comment regarding the thermalization. Of course, if you have any smaller scale structure in the surface displacement of the field lines on the magnetar, that will influence how the dissipation occurs in the closed zone, especially. But question: so there are constraints on the change in the spin down of the 1806 minus 20, the biggest flare source, before and after. So how well constrained is the change in the twist near the pole, the static twist near the pole, after your event?
How well constrained is the twist near the pole after the event?
Yeah. I mean, how close does the twist go to the pole? I guess that's one way of phrasing it.
Well, the magnitude starts to inflate when the twist is of order 1 radian or so. So at the point of when it sort of the giant flare comes back in, I guess it would be of order 1 radian.
But for instance, you can have twist exchange across field lines by reconnection and so on during the event.
Can I have twist? I guess so, but I haven't looked it up differently. Yeah.
You have one quick clarification and then one question. So the quick clarification is you mentioned at some point the shock and there was a guide field. So I wanted to understand that the guide field had nothing to do with the shock, or whether I was missing something fundamental.
No, I was thinking about like reconnection in the shock.
So behind the shock. So this would be the reconnection that is behind the shock, is a zero guide field reconnection. And
yeah, so around in that region over there. So if there's reconnection happening behind the relativistically moving outer region.
Okay. The other question, yes, so if I understand correctly, both the residual thermal energy that you have in the fireball confined and in this tail, it both ultimately comes from field dissipation in the same reconnection layer, right? So I was wondering whether this factor of 10 that you have from, or this, if it's 10 from one fraction to the other, whether that's controlled by the latitude of the twist and where this opens up into reconnection, or whether there is any insight into what determines this partition.
I'm pretty sure the numbers, I don't know if the fractions would change by a lot, but definitely the numbers would change according to where the twist is happening and how big the twisting region is. But yeah, I haven't done an empirical study of different twist angles over here.
Thank you.
Okay. So before the flare, the manuals may already have some net charges. How would the result MHD simulation be affected if you?
I have net charges.
No, but MHD would not have net charge, right?
Yes.
Neutral everywhere, right?
Right.
MHD simulation is, MHD is neutral. Is that right?
Right. I didn't. Sorry, I didn't.
Well, but one thing, the reality is that they already have some net charge distribution, not neutral. How would the result be modified? Oh, because you have twist, you have net charge. No? You have some net charge. You produce. You have current. In your case, you don't have. I'm saying you don't have charge.
No, I don't have any net charge here. Right.
Reality, there may be some charges. No? Well, you have you twist the field is twisted. You have current, and you may have some.
Mm-hmm.